Hi, everyone. We are looking at Chapter 7 of the Introduction to Statistical Learning with Python today. This chapter is kind of like the bridge between our discussion of linear models and our kind of discussion of like completely nonlinear, kind of non-parametric models. These are models that look like linear models in a lot of ways. But maybe have quite a bit more flexibility. So yeah, and in particular, we're talking about splines and gams, which I think are both funny words. Um, and so I wanted to start. I felt like we had a lot of different models presented in this chapter, and so I kind of wanted to set them out hierarchically so we could get a sense of like kind of where they all fit in together. Um, I would say of the ones listed here, kind of splines are like maybe the most interesting and the most like widely applicable. Uh, and then I think I'll touch on it maybe a little bit this week, but more next week about general additive models, which all of these can sort of feed into. So I've tried to visually represent this with the card shoots, but uh, so all of these can feed into generalized additive models, except I'm not sure that local regression can. That seems like its own um, kind of process. But if anyone knows uh, otherwise, you should let me know. They can all be represented with a basis function. Well, not all of them. Smoothing splines can't be represented, I don't think, with a basis function. But otherwise, all of them can be represented with a basis function, which we'll see is just kind of like a simple additive model where you're kind of adding functions together rather than just observed data. And they also all have this nice property of having a relatively efficient leave one out cross-validation formula. So they're, like by themselves, like kind of, moderately computationally intensive, but because there's this sort of analytical solution to the leave one out cross-validation, you can use cross-validation to figure out a lot of the like hyperparameters, I guess we can say, that are important in these functions. So they're pretty useful class of functions here. Oh yeah, and I wanted to also mention at the beginning, and one frustration I have is like the book. I think in service of making it easy and having a consistent interface in the labs for us readers, doesn't advertise as well as maybe it could the sort of underlying functions. So the book package is wrapping a lot of functions and then kind of changing the interface. Obviously in real life you probably won't be using the book package, and so it's nice to know the sort of like what's going on in the Python ecosystem. And so I did pull these out. So we won't get to GAMS today, but this PyGAMS package is like a really, like if you just, it's kind of fun just to look through the, I guess my link is broken here, but just to look through the documentation, and you could fit like kind of any additive model you could imagine with this package. SciPy interpolate is, I mean, it has quite a bit of functionality, but like as far as this chapter goes, has some tools for fitting splines. And it is the underlying sort of engine for the book's functions that it uses in the labs. I looked through the documentation and the kind of examples, and I would not say it's the most user-friendly documentation. It's quite technical, or at least to me, it felt technical as a novice about splines. And it does have a different workflow than the scikit-learn workflow. It doesn't have this kind of transform centric workflow. It has its own thing. So we might be grateful that the book wraps it up for us in the nice interface. So I don't think I'm going to focus that much on polynomials and step functions in this kind of meeting, this discussion. I think polynomials, obviously, we've talked about, I think, in chapter 3, just linear models where some of the terms are raised to a power. Step functions are a little different, but and kind of moving us in the direction actually of splines, where a step function is a series of constant functions. So you see it's like a series of horizontal lines that are fitted over specific ranges. So these are both efforts to kind of add more flexibility to the linear model. I think they're like my interpretation of this chapter. I don't think it comes out and says it, is that like the splines are kind of like superior in almost all instances. I'm not sure why you would use a sort of straight polynomial function if you could use a spline instead. And I don't know if anyone has any, if that offends anyone, but that seems to be the stance of the book. The splines are the way to go. Oh, I've had a LaTeX error, I guess. But so the whole setup for most of these functions is using this, like, I think we could think of it as like a framework called the basis function framework. And so it's just a way to represent nonlinear relationships in the same sort of linear modeling framework that we're used to. So the nice thing about this is that we can represent these nonlinear relationships in this way, and therefore gain access to all the kind of usual linear modeling equations and tools. It's like really quite plug and play. I was kind of surprised. Like I was, well, I'll show on the next slide, I guess, but it just kind of works. But the the key difference, obviously, with this setup is that instead of like an observed, like in this case, a vector or a scalar or a vector or a matrix or whatever of observed covariates, you instead have a function that takes a covariate as an input. So you see, like, there's a sort of beta coefficients that we know and love, I guess. And then there's these B functions that take each observation as an input, and that sort of allows them to represent non-linear relationships, obviously depending on the function. Is there anything more I want to say about this? No, yeah, I think that's it. I was curious to kind of, I'd like to try to represent these things as matrices, since that's often how we interact with them on the computer. And yeah, I mean, it looks exactly like the standard linear model in matrix form. I was kind of, maybe that doesn't blow anyone away, but it kind of blew me away. But you see the key thing is there's this matrix of these functions, which is replacing like our x in the standard linear model, and it's sort of a n by k matrix. And I suppose if you added like an intercept, maybe k plus 1, maybe it should be k plus 1 here. And yeah, the formula for beta is even the same. Like, it's just this, x transpose x, x times y. So, small world, I guess. So the real meat, I would say, of this chapter is in the splines and the gams. Splines, I think most basically we can think of, they're just another class of nonlinear sort of wiggly functions. I think that's like the most intuitive way. They have quite a bit more flexibility than linear models. They achieve similar flexibility to polynomial models, so like the kind that we began the chapter with, but with much lower degree terms in the model. And so like in general, like the lower degree is good. In particular for like model stability, polynomials, high degree polynomials can do unusual things, especially towards like the tails often of the range of X. They will sometimes kind of like shoot off into the sky or whatever. So these lower degree polynomials are a little bit more stable. And so the way that this works is that we're fitting multiple low degree polynomial functions over preset ranges of the independent variable, the X. And do I have well, okay, so and yeah, maybe this is just repeating a little bit what I just said, but this kind of first most basic spline is a regression spline. I think so called because it uses the machinery of linear regression to kind of fit this spline. It can be kind of written down using the basis function framework. So it's, I would say, a pretty user-friendly variant. But yeah, so it's just a series of these polynomial functions connected by knots. So the borders between the functions, where one function sort of transitions into the other, are called knots, and constraints. And so those are additional constraints that we put on the function, often to control how they transition into each other. So the constraints that we saw in this chapter were continuity across like multiple sort of like derivatives of the response variable. So like we actually, we want continuity in Y. We want the lines to connect, and we actually want continuity in the first derivative, and I think even the second derivative. I should double check that, but of Y to get like a really smooth curve. So if you don't want sort of jagged lines connected, you want smooth curves that have both the same slope and the same second derivative at the point of connection. And I think well, maybe yeah, well, maybe I didn't include that, but there's a figure in case you're quite curious about it. Figure 7.3 is sort of illustrating the sort of effects of this series of constraints. You start off with sort of just a bunch of wiggles in space that are unconnected, and as you add constraints, you sort of get a more typical spline that we're familiar with. And yeah, so I think these are like pretty, like, I don't know, they're not hard to wrap your head around. But as and actually, when I started trying to use the SciPy interpolate package, I was like, oh wow, I don't understand these that well. But and in particular, trying to kind of match your number of predictors, your number of knots, and your degrees of freedom can be a bit of a challenge. And yeah, I think this is interesting. And I actually don't have like an intuitive grasp of it. So I did want to put this to the group. Maybe this is what Jack was talking about. I don't know. But so the way to represent like a cubic spline, which is kind of this like workhorse spline that's flexible enough for a lot of purposes, is to fit. And I don't know if you can see my highlights, but kind of this like typical cubic polynomial model down here, like we have x squared and x to the third. And then we add a series of what the book calls truncated power basis functions. And so this is what the truncated power basis function looks like. And And so in this formula, x is x, and then she, I don't know how to say that Greek letter, but that one uh, uh, is the knot. So each knot is represented by one of these. And the way this works is that if x is greater than the knot, like the value of the knot, then the function takes on this value. And yeah, I don't know. So the deal with this is that it provides this like smoothness. I think uh, yeah, it remains continuous at the first and second derivatives. That's like an analytical property of this formulation. But I'm not sure I had a great intuition for it. Like, so, and I don't know if anyone wants to like chime in, but like the idea is that as x goes past each knot, this is growing and growing and growing, but until it gets to the next knot, and then it goes back to 0 and grows and grows and grows again. And yeah, it wasn't clear to me why, and maybe it's just math magic, but like why that would produce smoothness exactly.
Right, so I think
Yeah.
this, so I don't actually, I'm not 100% looking at clear what happens when you move on to the next knot.
Oh,
But when,
okay. Yeah.
like, the idea in here is that when you get to a knot,
Mm-hmm.
right, and a knot is going to be an area where there's like a change,
Mm-hmm.
or like you're noticing kind of a change in the input data. So you want to do something slightly different when you get to this part of data. Then the truncated basis or power basis function kicks in and it
Mm-hmm.
starts impacting the data. But before that, it does nothing.
Mm-hmm.
So it doesn't have an effect. But that kind of goes back to say, if you make a polynomial regression, you learn all of the coefficients
Mm-hmm.
for the different transformed input variable. So like degree 1 has a coefficient, degree 2 has a
Yeah.
coefficient,
Yeah.
degree 3. And those coefficients are like, they're global. Like
Okay.
they're
Yeah.
just learned from data. And you don't have any other parameters, you don't have any other degrees of freedom. So you just have to
Yeah.
like set those. But then the idea with the spline is like, well, at different points of the data, you can let these different functions kick in
Mm-hmm.
and affect the variable differently. And this is like, I think it's Xi or Xi, like
So
the
yeah.
KS. Yeah,
Mm-hmm.
I don't know how to pronounce it either. But yeah, like the input value minus Xi, like if
Mm-hmm.
until that's until X is actually bigger than that value, like just nothing happens.
Yeah.
But
Yeah.
this is one of those things where I do think the formula, I don't know. I prefer to think of it the other way in words,
Yeah.
like don't
Yeah.
do anything until this point in the data. And
Yeah.
then when that kicks in, you're in this knot, and in this knot, do this stuff. But I don't know exactly what happens. I would think maybe what happens is that it does stop at the next knot, or it just gets as the degree of the polynomials going up, the higher degree just dominates. But I don't know exactly
Mm-hmm. Yeah.
how
I
it
mean, I found myself wishing that the book didn't like set out this formula, and in particular this like additive for I just kind of like I think that's what they were saying. Um, and so yeah, on my interpretation, I think basically as you hit each knot, like this is going back to zero because you're subtracting like if you hit knot one, and then suddenly your x minus knot one is zero, and then you keep going, and so this keeps getting bigger and bigger until you get to knot two, and then then you're back to zero because x minus knot two is zero. So like, but yeah, maybe I think you're right. Like the beta coefficients must kind of regulate that in a way that makes sense, but. Yeah, I don't know. I think it is. Uh, yeah, it definitely makes more sense. Like when you say it verbally, like okay, like every range has its own special, has its own special sauce, basically. But I think when you try to represent it like this, I don't know, seems a little unintuitive to me.
Yeah,
Um,
I think I do want to actually, like, not now, that that's something to put a flag in, or something, like
yeah,
to go back to
yeah,
how do the what like when the knot ends, like the next knot kind of takes over.
yeah.
But like in the actual formula, like how is that specified? But I wonder if something that kind of made sense to me when I was thinking about it was try to think of like, well, what kind of data would you like want to model
Mm, hmm.
with a spline? Like, why does it make sense that you want to have these these different things? And like age and wage is a good one, right? Because
Yeah,
people's earnings will peak in their like 30s, 40s, probably slightly drop in their 50s, and then tail like right down. So you wouldn't want to learn the value of the coefficients for like
hmm.
ages 30, 40, and 50 and 60 altogether.
Yeah, yeah,
You would want this spline
yeah.
type thing.
Yeah, it seems like you have to have some, theory about I guess you could just look at the data, but you have to feel like there's some discontinuities, I think, some in the slopes, basically. Um,
Yeah, I do
uh,
think as well, like it doesn't talk so much about like looking at your data in the book,
yeah.
but that is probably the most important thing in all of this, is to always like look at what your data's doing, or try to I don't know, figure out what you should do based on how your data actually looks, not based on like a model you read about, or
Right.
like
Yeah.
a thing you're aware of.
And
So it's a
and
good point.
I'm not I'm sure this is like a really stupid question, but something that popped up to me when I was trying like understanding the regression spline formulation is I was wondering how this formula would extend if we're handling multiple variables, like
Hmm.
if y depended on both x and z, and I wasn't entirely sure how it would extend to that in terms of like even placing the breakpoints and such.
So I think that's what GAMs uh, are for.
Oh, okay.
Um,
Okay.
yep, yep. So,
Oh,
um,
great. I haven't
and
read that
yeah,
bit. That makes
yeah, because
sense.
that would be quite a disappointment. I think if you could do splines, but you only get one covariate. Uh, and yeah, I'm not sure how. I mean, I'm looking at the GAMS part. I mean, I think. Um,
I think on how it extends to multiple variables, it's like it gets quite hard to visualize, obviously.
yeah.
But say if your like knots spans along X, like the age range, that's like just a line, like geometrically, you
Mm,
can like draw a line along the X-axis, and you can say like in this like shaded region, the knot takes effect. And then in the higher dimensions, it will be like firstly a plane. So you'd be saying like in this plane rather than
yeah,
like in the boundaries of this line.
right.
Um, this is what I'm thinking. I haven't fully read the GAM thing, like I said at the beginning, but you're saying in this plane, these are the values.
Yeah.
And then as you get higher, you'll be in hyperplanes.
Sure. Yeah.
So, like 3D, 4D, 5D, and all this stuff. And you won't be able to visualize it at all. And
Yeah.
probably won't be able to even like fully understand it, but you
Yeah.
kind of can trust that it works, kind of just by like,
Right.
I don't know, the numbers being good in the model or whatever, but it's quite
Sure.
difficult, yeah, to
Sure.
conceptualize.
Sure. No, thank you. Thank you so much.
Yeah, and I mean, I guess we're not on get, and I need to like kind of dig into it a little bit either. But yeah, I think I was struggling to understand their limitations, like if they're just yeah, and I don't know, I guess we'll talk about that, or well, I guess I'll miss it next week, but I'll watch the video, I guess. But uh uh yeah, like if you're
Limitations with the
just
splines is that.
or well, I guess I was thinking of the GAMs, like since they are just additive, like they're just adding. I don't know if you're allowed to interact. Different covariates. I don't see why you couldn't, but like, it does seem like it would get pretty crazy pretty fast if you had, you know, knots for every combination of covariates. You would, I don't know, just feel like a lot of parameters, I guess. But yeah, I guess we're not quite on that. Okay.
Yeah, you need a lot of data too, because
Yeah.
you
Yeah.
wouldn't have combinations or many values in combinations of like more variables, right? So yeah.
And so a footnote, I guess, on natural splines. So these are just the same regression splines. They have an additional boundary constraint. So at the tail, so at before the beginning, before the first knot and after the last knot, they're constrained to be linear. And so this helps with the behavior that we sometimes see in sort of unconstrained splines, which is this tendency to kind of do unusual things at the end of the range. And so yeah, this is just a figure from the book showing in blue sort of a standard spline, and you can see it has a little bit, it looks about the same, but the uncertainty intervals are wider there at the end. And the natural cubic spline has those additional constraints, and so therefore has less uncertainty. And I guess in general, like one idea in this chapter is like, the more constraints you're adding, you're kind of buying yourself like some more degrees of freedom, and so like maybe a little less uncertainty, but at the cost of kind of constraining your model. Okay, so the kind of last extension of splines are smoothing splines, which I thought were kind of cool because of their connection to what we did in the last chapter. So they're just like a regularization technique for splines. So like whereas in chapter 6 we had the lasso and the ridge regression to try to regularize the coefficient values in our linear models. This is kind of the same, like really basically like almost exactly the same thing in the context of splines. I don't believe that these can be represented in the sort of basis model sort of form, and I don't think they even give us any representation, like any mathematical representation of it. And maybe maybe that's okay, but yeah. So yeah.
Oh no, sorry. Keep going.
Yeah, I mean, so it's like the exact same process as with ridge. So we're looking for a function, in this case, g, that minimizes this quantity. So the residual sum of squares plus this extra thing. And so like if you remember in ridge regression, it was like the same deal. We were trying to minimize the residual sum of squares plus this what is it, shrinkage coefficient? Is that what it's called? Tuning coefficient, I guess. But whatever, it's a coefficient that controls how flexible you want the model to be. But so in the case of ridge, it was encouraging the betas to be small, and especially encouraging the big betas to be small. And in the case of smoothing splines, it's encouraging small second derivatives. So like, and in particular, the sum of the second derivative over the whole function. So if you think of the sum of the second derivative is basically an indicator of like how wiggly the function is. Like if it's the slope is changing, all the time, then you're going to have a high value, and if it's just a line, you're not going to have it's going to be 0. And so basically you're trying to minimize that. And so the value that you assign to this tuning parameter or shrinkage parameter sort of controls how sensitive you want the model to be to sort of like smoothness versus flexibility, basically. So yeah, I don't know. I was honestly quite tickled by that. I don't know. It's just nice to see the same thing twice. But so
I think you were right, Cory, when you said it's like a shrinkage parameter.
Yeah.
Like you do tune it, like it's a tunable parameter, but it controls shrinkage. Yeah, just you had it right first time, basically.
Yes. I was tempted to include the GIF of the Seinfeld episode about shrinkage, but I decided against it. Although maybe I it's just as bad to mention it maybe. But yeah, so just like Jack just said, like conceptually, it's like a shrinkage parameter. It penalizes like more complex areas of the model. So if there's a lot of up and down, or then that area of the model is going to be sort of more highly constrained by this function. And so the trade-offs with this, you basically get to pick this parameter, or you can try to obtain it by like cross-validation or some other method. Is that as the tuning parameter goes towards 0, we have high bias and low variance. So like if you think tuning parameter is 0, then you have no penalty. Then the model is just like literally is going to fit the points. I think it will just go from point to point, because I think the way and I didn't mention this, but the way smoothing splines are set up, I guess, is that there's a knot at every observation, and then those kind of get smoothed away. But the basic setup is that there's a knot at every observation. So if you don't have any penalty, then you will just have lines between points. So that will and I always second guess myself here, but I think I want to say that's high bias, low variance. You're overfitting. You've kind of missed. You're sort of over relying on the data.
I think it should be the other way, right?
You think it should be? Yeah.
Because the book talks about the case where it says like if you wanted to get like the loss function, like minimize the loss function, like get RSS essentially to 0, like you can interpolate between all of the points. It's like you could just draw a line through all of the points. And obviously if you do that, like your model is like super squiggly wiggly, like it might perfectly fit the training data, but it's so that means it's like very low bias. Like it can in principle capture any relationship, and bias is whether in principle the model can like fit the data. So when you're super squiggly, you have like super low bias. Yeah, but you have like the highest variance possible because you've just completely fit the training data in like a completely non-smooth way, which is really bad. Like it won't look like that in testing kind of thing.
Yeah. I don't know. I have a hard time wrapping my head. I think the idea of like performing well on the training set and badly on the test set is like pretty intuitive to me. It's not clear how, in my mind, I don't have a good like model of like how that relates to bias and variance. If it's like, performs poorly on the test set, is that a case of bias or variance? But yeah, I think the way you described it makes sense. Like it's like, in principle, could have sort of captured the right relationship, but the chances of it doing that are low because it's just gonna pick up whatever noise is in the training data. So yeah, that makes sense. So I'll reverse that. I think you're right.
I think this came up in one of the ones where I was away, and on like the bias thing, it's probably, or in my head it makes sense not to think about it so much about like individual instances of testing error or training error. It's like if your data is like a parabola, like it's shaped like a bullet, like inverted. It's like that's a quadratic relationship. So if you fit a model that is just linear against that data, the linear model has quite high bias because it cannot in principle model
Capture that,
that quadratic relationship. And yeah, it will have quite low variance in that case. Like you tend to trade them off. Whereas if you have like a super high degree polynomial, it can really easily fit that parabola. Like it will have absolutely no problem of doing it in training. So its bias will be very low because it can model that type of relationship. It's just, it will fit all of the noise and it will fit everything. So then it will, there will be a lot of variance. Like you'll learn stuff in training and then your test error will be just like all over the place.
Yeah, that's helpful to me. I like this idea of like, you know, being able to, in principle, capture that relationship. I think that is helpful. And yeah, I do remember. I think maybe on chapter 6, we also we got sort of talked into a bit of a confusion hole by about this bias variance issue. So maybe we should revisit that. And then, yeah, the last little note about these smoothing splines is how the this tuning parameter, the shrinkage coefficient, kind of affects the effective degrees of freedom. This is what they're calling it. Like, I guess the sort of like raw or like technical degrees of freedom is going to be n, but because of the smoothing, the effective degrees of freedom decreases as lambda increases, and so like at the limit it can go as low as 2, you know, which is good, but I guess there are trade-offs, obviously. Oh no, well that's a bummer. So this is I'll fix that eventually. But so this, and you know, I found this a little mysterious, but this is the if you want to calculate the degrees of freedom in your smoothing spline, you have to use this sort of arcane technique. And so this is on page, I don't know, it's equation 7.12 and equation 7.13. But you basically have to add up the values on the diagonal of this matrix, which is called S. And S, I think you sort of calculate from like an equation that's not given to us in this context. So yeah, so you so you know, I think if you find yourself calculating the degrees of freedom, you know, sort of analytically, maybe you've maybe you should turn back. But yeah, so there is a way to do it, I guess. And it is a little tricky because I noticed some of these packages you have to you specify your degrees of freedom as a argument to the spline function, and so you do actually like have to know like how many you know, and maybe the smoothing splines you don't have to, but yeah, it is a little bit of a pain, I think. Let's see. And so, yeah, I have some last remarks, I guess, about the computation stuff. And you know, I don't know. I don't understand it that well. But so this I understand. You know, this is basically in the computation splines in the labs. The book kind of does this nice sort of wrapper around the SciPy interpolate package. So it looks exactly like the model fits that we've seen in all the previous chapters. And so this, so here I have the model results, which I guess are, you know, I think like fairly straightforward. So I think these are, so if you have 3 knots, and I think this is a cubic spline, I believe these are the, well, so this is maybe a intercept. These are the, oh, this is truncated. I think I think it perhaps is truncated, but I think this is the intercept. I think these are the polynomials, and then these are the sort of power basis function coefficients. I think that's right. Maybe this isn't a cubic spline. I have to double check. Yeah, but so that, that's that. So that's not that hard to wrap our heads around. So now moving more towards this sort of SciPy module. So this is still using the book wrapper around this function called bspline. And so this is the book's code. And so I wanted to look at like the model matrix. So this is the model matrix for this model. And yeah, so it has, I think it has 6, 1, 2, 3, 4, 5, 7. So I guess k plus 4 for a cubic spline. So yeah, I guess 7. And yeah, you can see like it is like literally just just observed x's at each knot, I think, right? Like, is that I think that's right. Although I don't know why, because these are age values. So yeah, I think part of the reason I put this on here is because I was like, maybe they can help me figure out what I'm looking at. But
isn't it? So you've got for the B splines, you'll have the like however many knots there are.
Mm-hmm.
Each of those will have a additional degree of freedom, I think, because well, depending on the degree of the polynomial. And then you have one for the intercept. But these things, they should be like ranges of values of the input parameters, each having their own. So yeah, shouldn't they be coefficients of like for those values of the input parameters that fit inside like that knot? This is the coefficient, like depending on what data is being modeled. Like, is this still the wage data?
Yeah, this is the wage. Yeah, this is the age and wage data. Okay, so maybe these are the although I don't know why there are rows, I don't know. So I guess I was a little perplexed by this. I didn't spend that much time looking at it. But
yeah, what are the rows? Are they?
I think they must be well, so yeah, so I think they must be observations because I just did the head method. So I think there's way more rows. I think they must be observations, but they're not observations of age because they're decimals. I don't know. So maybe that's something to look into. I'll put that on my list. And then my kind of final failed effort here was to just try to use the SciPy package sort of without any guardrails from the book. And I, couldn't really figure out how to do it. I looked at it for a few minutes, but the documentation is definitely written for spline enthusiast. And so I was trying to create a model matrix. I understand that perhaps this function might be useful in doing that. And so this thing you can give it, an X and a Y variable, and it will give you, well, in principle, I guess, it will give you the knots, the coefficients, and then the degree of the spline. So that is useful. I had a hard time getting the pandas data frame to work with this function. And so I haven't, so that's why I use this like kind of fake generated data, but yeah, couldn't get the pandas data frame to work with it. Tried to like turn it into a NumPy array. So yeah, so, another room for further investigation, I guess. But yeah, so that, kind of the extent of my, but I think this on some level like makes more sense to me. Like I understand, okay, I have an input and an output. I'm getting these values from this algorithm, I guess, and then I can build the model matrix from that. So, but yeah, it was a little technically challenging. So that's
What's the
that.
S equals 0 there? Do you like that's being fed in rather than received?
Yeah, what was that? I think that's a smoothing parameter if I remember.
Like
Let
the
me,
lambda or something.
yeah, I think it's the lamp. Yep. I don't know if it is like I don't know if it's using that exact approach, but it is. I'm pretty sure it's a smoothing parameter. Let me, yes, a smoothing condition. And it
Yeah, I
does,
think it's
to me, it
seems
does
like
look like like it looks like lambda.
yeah, it seems like the type of thing to sit and read the documentation for, for like
Yeah,
quite a long time for. Seems a bit
yeah,
involved.
yeah. It's funny because the documentation is like great at some level, but it's quite dense. So yeah.
So yeah, you
Okay.
put in your inputs, your like response, your like
Hmm.
features, your response variable, you put in smoothing parameter, you put in the degree, and then you get out your knots coefficients degree. And then
Yeah.
you feed those into the actual B-spline.
Yeah.
Yeah, interesting.
And yeah, that I printed out the coefficients for the curious, but yeah, so that's it. You know, GAMs, you know, I think are, you know, basically the multivariate extension of these splines, and the other basis function models. So I guess we can tackle that, you know, next week. I'll be sad to miss it in here. So maybe I'll stop. Maybe I'll stop the recording.